My name is Alexis Soto, and today I want to explain a idea in computer architecture based off our class CS61. And this will be why CPUs don't always make your computer feel faster. We usually think performance is all about the processor, which would mean higher gigahertz, more cores, and just everything overall being faster in general. But even the fastest CPUs spend a lot of time waiting. The main reason this happens is because of memory. One little example that I want to give to try to visualize this is when it has to do with your brain and when you're in a flow state of creative thinking. Let's say that you have a lot of ideas and you're trying to write them all down as fast as you can. I don't know if this has ever happened to you, but maybe you're in a flow state, you have a lot of ideas and you're trying to write them down, and you end up not being able to write the ideas down as fast as you're coming up with them. Essentially, your hand gets stuck trying to catch up to your thoughts, and this is, in a way, slowing you down on trying to get everything stored in a place where you can go back and remember it. This is basically the same way computers work. In this case, the brain would be the CPU, and writing down the ideas is the RAM, which stores them. The key point to understand here is that a CPU can only run as fast as it can get the data. It doesn't really matter if the CPU is extremely powerful, because at the end of the day, it's dependent on how fast it can input and output this data. But why does this happen? This is the gap between CPU speed and memory speed that has happened over the course of multiple years. Basically, since they first were created and invented to up until recently modern times. The CPU processing power has been able to follow Moore's law, in which it's able to double its amount of processing speed every 1 to 1.5 years. But in comparison, memory has not been able to make the same advancement in performance, as memory has more or less stayed around the same speed, while CPUs have drastically increased in speed. And this gap right here is what we call the memory wall. I would like to explain it using this example right here. Basically, think of the CPU as being this really slow car, and every year the car gets faster and faster and faster with each iteration. And as it's running at a race, it has to stop by and get some service done by the pit crew, which would be the memory. As we can see here, the pit crew is made up of these older crew, which doesn't really know much of what's going on. But since the car is slow, they kind of go hand in hand and are able to make it work. But as I explained before, the car has been improving year after year after year. So after 5 years, we have this really, really fast race car. The crew itself has only been able to improve a little bit. We can see here that now they're a little bit younger, and maybe that allows them to move a little bit faster when it comes to part moving and making sure that the car is operating at its maximum speed. But they're still kind of clueless on what's going on, so their knowledge has more or less stayed the same, but they are a tiny bit of an improvement. However, this makes the race car have to wait for the crew, as the car can complete its laps really, really fast, but once it comes for its change of tires and maintenance, the crew ends up slowing it down drastically. Here's what's really happening. The memory itself is really slow in comparison to the processor. Here we see that each square represents a cycle in time, and this would be the amount of time it takes to get information on this end to be able to output it back on this end. So the CPU is able to cycle one after the other after another really, really fast. And here we can see that these lines indicate when they match up and sync and allow the CPU to process the data. But as the CPU is waiting for this memory to access and return the data, the CPU ends up having to wait throughout a lot of its cycles. This ends up making it so that the CPU is essentially just wasting time and stalling throughout this whole period that the memory has to get its information. To reduce all this waiting, computers use something called a cache. The cache is essentially a really tiny version of that memory, but it's connected really close, almost directly to the CPU. And because it is so close and really small, it is much faster for being able to transfer data to and from the CPU and this little slot of memory. I'd like to think of it as if we had a chef that was right next to a small fridge with all the ingredients that it could need. The chef is able to very quickly pop in, grab its item, and come back and continue cooking. This would be called a cache hit. But let's say the chef needs something that it doesn't have in the fridge and is located in a grocery store which is farther away. Because it doesn't have its ingredient right away, this would be considered a cache miss, because now it's having to take a longer trip out to the grocery store, get its item that it needs, and then come all the way back to the kitchen. This is also the same case for computers. Data in the cache is able to run programs extremely fast because it has basically direct access to the CPU. But when the data that it needs isn't readily available, it has to make a longer trip out to these other cache locations, in which it takes a bit longer and is what is considered the cache miss. The good thing about this is that modern CPUs have multiple caches. They go by L1, L2, and L3. So in this case, L1 is the really small fridge that has all the necessary ingredients in the meantime for the chef. L2 would be like a pantry run, where you have to go a little bit further, maybe to another room, to look in a pantry where you might have the ingredients that you need. And the longest destination of them all would be L3, in which, in this case, you do have to run to the store, gather the supplies, and then come all the way back to the cooking area. Each iteration is slightly slower, but they do get much larger in the amount of space that you can store. Now, one way to go about this, and a good question that seems to be misinterpreted, is why adding more RAM does not mean faster. For example, going from 8 gigabytes to 16 gigabytes of RAM wouldn't really make a difference, because as we can see here, their speed in megahertz is same for both the 8 gigabyte and the 16 gigabytes. Essentially, this is like when we were writing in the notebook. We're writing at the exact same speed, but the size of the notebook just got bigger. So instead of this tiny notebook, we're now writing in a bigger notebook. So in this case, RAM would help you open up more applications at the same time, but it doesn't really make the RAM any faster. But what would happen if you do open up all these tabs or applications? Let's say, for example, you open up 50 Chrome tabs. When you do that, your computer seems to be slowing down, but this isn't because the CPU is overloaded. Instead, you've basically ran out of that little bit of storage that caches allow you to hold. The data that these tabs need keeps getting evicted from the cache and is forcing the CPU to use all the other methods of slower memory, which would transfer over to L2, L3, or maybe even other parts of RAM. This slower memory makes it so that the browsers become laggy, even though the CPU is technically considered very fast. This is again a recall to the memory wall. Even though the CPU is working at, let's say, 20%, the computer feels really slow because of this memory restriction. So to put this all together, the number one thing that we have to keep in mind is that CPUs today are incredibly fast, but memory hasn't really kept up with their advancement. Because of that, CPUs often spend a huge portion of their time stalling and waiting for the memory to come back with its data. Because of that, we were able to come up with clever ideas like L1, L2, and L3, in which the CPU is able to access this data faster because it's readily available. However, the size limitations make it so that if one gets full, it does have to resort to these other slower forms of data processing. This limitation between CPU and the RAM or the memory is essentially the main idea of a memory wall. The real reason why faster processors don't always mean faster computers is because at the end of the day, the computer can only really go as fast as the data allows it. So in our case, our race cars are really, really, really fast, but our pit crew is just too slow to compete in the race.